Yes. Okay, so if you notice today, we go and download the repo from GitHub. There's only a notebook. Okay, so we're not going to be introducing. There's no lecture for the next 2 weeks. We're going to walk through this analysis, and we're going to try to do it end to end. Okay, so in class, we'll be working on a data set that we pulled from Kaggle. It's kind of like a toy problem, but at home you're going to be doing an analysis on a much more realistic leukemia data set that you have to download yourselves. So so today it's pretty much going to be like getting to know your data, you know, feature engineering and all the such. And next week we will start to do the actual prediction. So the idea is that you guys will take the lessons that the patterns that we use in this analysis and apply it to the real data. And that we'll be touching base regularly, but the idea is that you guys are going to go off for the next 4 weeks, right? So there's two weeks for this leukemia toy problem. Then in the next following week, we're going to talk about a little bit of computer vision and convolutional nets. And in the fourth week, in the one after, I'll touch on some more advanced topics like GANs, and we'll see where we are then. But on that fourth week, we'll have you guys like present the models that you've made on the real data set and maybe compare, you know, their performance. The idea is that by the time you get to that point, you did a whole end-to-end analysis all by yourselves and even did some interpretation. So I'm really excited about the next I guess 4 weeks. And yeah, so let's get started. So I'm going to be presenting sort of a toy problem. Okay, guys. So last week I mentioned at the very end how to access, how to get data off of Kaggle with their API. I hope you guys looked into it, but if not, we're going to walk through it now. Okay. So today we're going to be looking at a leukemia data set. Okay. It was generated in 1999. The results are published. So, you know, we can compare with some published work. Granted, it's from like 20 years ago, but fine. So this data was used to classify patients with acute myeloid leukemia, AML, or acute lymphoblastic leukemia, ALL. Okay, so it's a classification problem. Okay, and the predictive we have are gene expression. It's gene expression data. Okay, so our exercise is to develop a model that discriminates between these two classes based only on this gene expression data. Okay, and then for fun, maybe we'll compare our models at the end of the second week with some of the published results. So we'll see if a group of students can outperform some PIs that published in Science. I'm pretty sure ML has progressed since then, so hopefully we get some exciting results. Actually, I'm eager to see how that plays out. Okay, so any questions so far? Yeah? All right. Okay, so I'm just gonna go ahead and I'm just gonna install all the requirements. You don't have to worry too much about this. You'll see this new install here for Kaggle, right? Okay, so everything's already satisfied. Great. Okay, so I really encourage you guys to follow along with me here. This whole notebook, you guys are going to be going step by step with me. Okay, so to download the leukemia data set, you're going to need a Kaggle account. Does everyone have a Kaggle account? You can speak up if you don't. You can create it right now. So I'll walk you through it. So you just go to kaggle.com. I'm already there. If you're not, if you don't have an account, you just land on the login page and create an account. It's pretty straightforward. Okay. Once you do, we're going to need an API token. Okay. And so up in the corner here, if you go to your account settings, pretty sure nothing sensitive is showing here. You go ahead and create a new API token. All right. And man, I guess I should make a new one so I can make it with you guys. So I'm going to expire all my old tokens. Okay, expired all tokens. It gives you a message. I expired all the tokens. I'm going to create a new one right here. Okay, so notice that something got downloaded. It's called Kaggle.json, right? And it's telling me where to put it. So you would do the same. So the tilde here, that means your home directory. So it's telling you where to put it. It's telling you in your home directory, in a folder called .kaggle, put this kaggle.json file there. So I'm going to go ahead and do that. You don't see my other screens, do you? Okay. Let's share the whole desktop then. Okay. So I just do it from the terminal, but maybe one of you guys can demonstrate how to do it in Windows. But what I would just do is copy from my downloads, not documents, downloads, this Kaggle file, right? So it's called Kaggle 2. Yeah, Kaggle 2. Copy it into my home directory in a .kaggle folder, and then in a file called kaggle.json. Kaggle.json. Okay, so I just did that. So maybe I can show you guys what it looks like. It's just a text file. You'll get to see my API token, but I doubt anyone can memorize it that fast. So more Kaggle and then kaggle.json file. It's just a text file, you see, and it says your username and some key. So
would it be helpful to show this for the Windows people? Because I just did it. I can show them.
Great, that'd be great for you. Let me relinquish the share.
Okay, cool. All right. So I'm going to do this for the Windows folks. So go to screen 3 here. Y'all can see my Jupyter notebook now. Right? Okay. All right, good. So make sure you go make your Kaggle account. So I just got to mine here. So go to Kaggle. It'll, have your username here, right? So just like Dan was showing, same procedure. Where you go to API here, it's under your user settings, create new API token. This will just download it for you, right? So you see it here. It'll say open file here if you're on Edge or Chrome. Now that is in your downloads, right? So all you need to really do is go over here to like your, this PC, see users, whatever your username is. So this is like your home directory, right? So I actually already have this here, but you shouldn't already have it there. All you do is right click, new folder, and then name it .kaggle. All right, so take that file that you got and just put it in here, right? So go to your downloads, copy, back, paste. And now you go back to your Jupyter notebook and this should work. Yep, and you can see it does work. All right, any Windows folks have any questions on what I just did there? Okay.
Okay. All right, then. Let's share my screen. And it's the notebook. Okay. So yeah, it's important. Please stop me if you haven't done this already, because we really can't move on if we do this. So the API uses these functions, this authenticate. It's going to look for that API token where it's expecting to find it, and if so, then it does all the login for you. And all you need to do is tell it where to put the data, right? I'm just calling it data here. It's going to be a folder called data right next to your notebook, wherever your notebook is. And you need to tell it what the data set is, right? It's the user and the data set. And then it'll load the files right here where you told it to. So let's go ahead and run that. Okay, finished running. So I believe if I look here, so this folder wasn't here previously, this data folder, and it's downloaded these 3 files: actual CSV, a training set, and they call it independent. That's the validation set or the testing set. Okay. The actual, I wonder if I can just open it like this. Yeah, I can. So the actual file, it has all the outcomes, right? So we have all the patients here. There are 72 patients, and we have their outcomes, either ALL or AML. Okay. So I could close this. I don't need it. And if I look at the training set, this is probably a terrible way to look at it. Don't worry about it. We'll look at it in the notebook. So I supplied some information here. There's the first 38 patients are part of the training set, right? And the independent testing set is the remaining 34 patients. Okay, and this is exactly how it's partitioned in the paper, so we don't have to worry about matching patients and whatnot. We're just going to use exactly how they are. So also what you'll find is the values of the gene expression data has been rescaled. Okay, so let's have a look at it. So right in here, we're going to now download. So labels, I'm going to use that actual.csv to give me what the labels, the outcomes are. The test set, I'm just going to read the independent.csv, and for the training, I'm going to read the train CSV. So so the first task here, and I'll bring up the chat board here. Oh, I have something in chat. Okay. All right. So is everyone so far up to here? Yes. Okay. So what I want you to do is I want to look at the training data, right? So it's a pandas data frame. So we can use the head function to just have a look at the first few rows of this data set. And I'll have one of you guys drop that in chat, and I'll and then we can just do it right here. So right here, don't be shy, guys. This is a softball. Yeah, yeah. There we go. Train head, right? All right. So let's just run it. Okay. So if you look at it, let me make this a little wider. Okay. So if we look at it, this is the way that the data looks like. So here are the rows, the first 5 rows. There's 78 columns, right? What we have here are the genes, right? The gene description. In this column, some gene ascension number. I don't work with like genomics too much. I had to look it up what they were and what format they are. We figured it out. And And I'll explain what that is later. And then this 1, 2, 3, 4, 5, those are the patient IDs, right? And this is the value of that gene expression, normalized, right? So it's minus 214 for patient 1 for this gene. And call here, that's the outcome, right? So it's kind of like written in multiple places. So you can see this is not very neatly formatted, okay? So yeah, the testing set is formatted the same as the training set, fine. Okay, so notice that the gene description and ascension numbers are given along with a count and outcome for each patient. The patient outcomes are also provided in the actual, and I think it'll be more convenient to use the outcomes in this file and delete the call columns in both the training and testing sets. So my question to you is, what are the observational units of interest? What are our samples? Like, yeah, what are our observations and what are our features? And how should we format the data? This is like a question to you guys. So what are the features? Like what is the data that we're going to use to be, what are going to be our predictors for predicting the outcomes?
Is it the gene accession number? And I'm not sure.
Yeah, like these are the elements, right? The genes.
Yeah.
The genes are the things we're going to use, right? Their expression values are the things we're going to use to make predictions, right? To predict these outcomes. And so the observational unit is the patient, right? So the patient has a number of values for each one of those genes, right? Mm-hmm. And the outcome is the final feature or attribute, right, of that. So the way we've been looking at it, like for you R folks, or in all the lectures I've had here before, we kind of have our samples as rows, and we have our features as columns, right? So we need to format this data to look that way. And also these call columns are completely unnecessary. So so kind of like a softball one is like, what is the code here to remove the call columns from these test and train are these pandas data frames? So guys, I'll have you guys write in here a bit of code that would remove. How do you remove a column in a pandas data frame? Yeah. So, well, what is a function? What is a pandas function that'll remove a column? Drop. Yes. Yes, exactly. So at some point, I'm going to need something called test.drop, right? What am I dropping? What am I dropping? You're free to look up, start Googling it. You're free to look up what the syntax is.
All the columns that have call word in it.
Right, so some sort of columns, right? And we're gonna, and the axis, the axis is like in columns, right?
Yes.
Right, so what are calls then, right? You're saying all the columns that have the word call in it. How would I sort of, calls is what?
It's an old, it will be an array type. It will be old calls. So we can do call and from 1 to 37 combine call dot with that number.
So yeah, like try to type it in the chat
Yes,
so I can.
sure.
So yeah, it's called call.1, call.2, call.3. How do I select those columns? So does everyone understand what the question is so far? Like what we're trying to do? Like, please let me know if you're like, what is he talking about? We want a way to pull out all the columns that will basically have the word call in it. From the columns in test, for example. Are you guys furiously trying to type it out, or? Okay, let's see. Calls equals call dot. Let me pull this into here so I can. Oops. No, it's not letting me. All right, I'll just type it out myself. So he's got a list comprehension, right? So we're saying something like for I in the range of 1 to 38, and then what? We're going to say the string call. Now we have a dot here, and that might be bad. A call plus string I. So does it, and then calls insert 0 call. Calls insert. Am I misreading it? Calls insert. Is that meant to be a new line?
Insert. Yes, yes.
Yeah.
Yeah, it's at the new line. Yeah.
Yeah. Okay. I'll put it as a new line. Oh, I see what you're doing. The zeroth one is now call. Okay. So okay, I'll read it out to you guys. So what he's doing here is a list is, sorry, we're marching through the numbers 1 to 38. That's what I is. And we're going to say, give me call dot 1, call dot 2, call dot 3, right? And that's going to give us this call dot 1, call dot 2, call dot 3, right? So on and so forth. And then you notice the first one doesn't have a call dot, right? So that's what this insert is. We're going to insert into this calls in the 0th place call. So if I, let me just uncomment these out so that we can look at what calls is doing here. And then I guess I could just say calls. If we run this, you see the list is now call.1, call.2. So these are the column names that we're after. Yeah. I had something written a little different. So one of my issues with this is that there's magic numbers in here, right? We had to know that there's 38 columns, and you may not. And if that changes in the future, then this code will break. So maybe I had written calls is equal to, it's a list comprehension 2, but I'm going to say if call is in column, right, for call in, well, the columns call, so if for all the column names in test.columns, these are the column names, for each one of those, if call appears in it, then return it. If we do that, did I mistype? Call for call, sorry, return call. Yeah, so for all the column names in this column, if the string CALL appears in it, then return it, and you get the same thing. So was that clear to everyone what we just did? Okay, so we'll move on. And then we're gonna, just in here, we're gonna look at train, the top part of the head of train. So we could see, oh, there's a your code here. Oh, we have to do the same thing for test, for train, sorry. That shouldn't be an issue. I think since it's formatted the same way, I could say train, drop those very same columns in the train data frame. And then we're gonna only look at the train. So yeah, all those calls have been removed. Call 34, what is this here? Oh, because they're different. Yeah. Yeah, because they're different numbers, and exactly, it's a magic number. So calls is for the ones in test, and I need to do it again for train, for all the columns in train. This should work. Perfect. All right, you see, even it caught me. Okay, everybody good with what so far all we've done? So our goal right now is to get this data and like massage it so that we have all the genes as columns and the patients as rows, right? And get rid of all the unnecessary stuff. Okay. So we've gotten rid of those columns, and now it looks like we're pretty much there. We just need to sort of flip the order, right? Make the rows into columns and the columns into rows. So how would we do that?
We're going to transpose it, right?
Yeah, we transpose it. Perfect. Perfect. So I'll let maybe somebody else, what's the syntax for it? You could Google it, because I would have done the same thing. So for train. How to transpose a data frame. All right. It's a softball one, so we'll, yeah, train transpose. Yeah. Train.transpose. And is it in place? I hope it is. Let me just look at train now. Yeah, and it's been transposed. So great. I'm going to do the same thing for test, and I'm not going to retranspose train again. So this is going to be test, right? Transpose a test, and then spit out train and make sure it doesn't change. Yes. Okay. Great. So now we're looking good. We're looking good here. Here we have the patients in rows, and we have the genes in columns. But we have these, well, they're like bookkeeping rows. We don't need them, at least for the prediction. So we're going to go ahead and remove those all that bookkeeping data, but I mean, it's kind of a good thing to like save this. You know, I want to like save the order of the gene number so that later I can say, was column 0 this? I can just make it the column names, but I'll just get rid of it and just save a copy of this row. So I'll let you guys, how would I do that? I want to save a copy called like the gene ascension number. The gene ascension numbers are, I want this row, the data in that row. Yeah, because the next thing we're going to do is we're going to remove those 2 rows, that bookkeeping data. We're going to remove it, but before we do so, I want to save a copy of this. What do we got here? Train column 2. Will that work? I don't know. Let's try it. And then I guess we can just print out ACC now. Nope. Oh, I misspelled it. Balance syntax. Does it need this? Because that's from like R, right? Like just the comma by itself. Nope. It's like here, slices, none. So just those columns, sorry, just those rows, right? These are the indices.
Yeah, with the description.
Yeah, but we only want one. Well, this is fine. Sure, this is fine. It's in there. I literally just had this, just this one, but it's fine. So yeah, so see what we've done here. We've accessed just these row names, right? The indices. This is totally opposite of what you see in like R. So far so good, guys. Yeah. Okay, so I have it saved here. We'll use it later, maybe. But now I want to get rid of that bookkeeping data. I want to get rid of those 2 rows. And do the same thing for test, the same thing we do in train. So this should be familiar. This is, so I basically just want to drop those rows. It goes right here. All right. I think for the sake of time, because we already did something similar to this, we're just gonna, it's dropped, right? Just like we did before. So train, we're gonna drop what? We're going to drop 2 rows. So let's give it a little list here. And the first one's called, let's hope I don't misspell it, gene description. And the next one is called the ascension number. does everyone see what I'm doing here? So from train, I'm going to drop these 2 rows. And I guess I'll do the same thing in the testing set. So this is test drop. And then let's look at the head of train to see, make sure we did it all right. And we did. So it's basically, it's just starting from here down. So these are all the patients and these are all the genes. We've erased what the names of the genes are, but we've saved it. For now, it doesn't really matter. One gene is as good as the next as far as I'm concerned right now. So far, so good, guys. We've pretty much formatted the data. And this is, you're gonna have to do this every time. You have to look at the data that you downloaded, and they're all gonna have their nuances, and this can be a non-trivial task to do. All right, so yeah, let's take a second here to look at it. So I'm only showing the first 5 rows, but look, there are like 7,000 genes here. So I can't possibly like look at it all, right? And there's a positive and negative values, and this has to do with the expression data having been normalized, right? I actually don't know what the normalization is, but it's maybe mean centered, maybe it's around 0. I don't know how to explain a negative value. We're gonna have to look at that. So yeah, so let's move on. So now, let's focus on the labels. Let's encode those labels, right? So right now, the labels were the words ALL or AML. And just because I know when we're going to do some sort of logistic regression, we want those to be 0s and 1s, right? We need to binarize those outcomes. So let's make all the ALL outcomes 0s, and let's do 1s for AML. So I guess what we're going to be doing is we're going to be predicting AML, right? And we're going to use the labels. We're going to change the values and labels, I guess for fun, just to refresh everyone's memory. So labels is this. Labels looks like this right now. We want to change all of these. The ALLs, make those 0s. Okay. Also remember, this is every patient. So we're going to have to remember remember the first 38 patients were in the training set. Okay, so how would I change labels? How do I change the values here to 0s and 1s? So we're going to be changing labels. So it's going to be something like this. Labels of, I don't know. What is the function that we use to change one thing for another, the values? Replace, exactly, John. Yep, replace. So labels, replace. Replace what? What are we replacing? Well, I could pass it like a dictionary, right? I could say something like I want all the ALLs, I want them to be zeros. Right? Remember this from when we imputed? Like you can replace the NAs for something else or replace the zeros for something else. So all the ALLs are zeros and I'm going to make all the AMLs. Is that right? AMLs. I hope I didn't screw this up. Yeah, that's what they're called because I can't see AML. I'm pretty sure it's AML. Yeah, so this should change. This should change the labels. Let's just, oh, actually, yeah, I could just write right there, labels, run it. Great. I'm going to assume the AMLs worked out too. All right, so now that we have the labels, we need to get the training set and the testing set labels. So remember that we need the first 38 patients. We want to save those. Where am I? Here we go. The first 38 patients, we want to save them here in the train and the remaining in tests. So what would you do? Like labels. We want to pull only those first 38 rows out and save them. Yeah, we just did something like that over here, right? Where we pulled specific rows like that. So what goes in here? Label 0 to 38. We could do it that way. Yeah, we could do it that way. 0 to 38. Yeah, because 38 doesn't get included, right? Yeah, so it's 0 to 37. That should work, yeah. And then what do I write here then? Well, I guess what labels 38 to what? To the end? Yeah, just like that. All right, let's see if this works. Let's look at labels, train, and well, let's do another code block. Let's just run this and then make a new block here. Labels, train. So I don't look at the testing set. It's got the, yes, because it's the patient numbers from 1 to 38, but it was the 0th row to the 38. So yeah, I think that worked. I mean, I really doesn't really matter too much. And this one went all the way to 72. Okay, so that worked. I actually wrote something a little different. This is a little more elegant, I think. Your answers. I had written something like labels train is labels where the index label index, it's exactly what you're saying, but label index is less than equal to 38, something like that. I think this is a little more elegant, so we'll keep that. All right. All right, so let's just get rid of this. I don't need it. Okay, so now we formatted the labels, we formatted the predictors, or what we hope to be predictors, and now we can start like treating missing data. Okay. So remember before when we said looking for missing data is more than just simply looking at NAs, right? Like you have to look at data and see if anything doesn't make sense. And then we have to think about how we're going to treat this missing data. There's a lot of different ways, but for now, I think that if we use what we've been using in the past, which is basically replacing a missing value with the mean that's in that column, I think is reasonable here. Maybe a more a better way would to be no, because you don't have clinical factors. Sorry, guys. So normally I do it as I look at patients and look at their clinical covariates, and then find those patients who's have similar like demographics or similar clinical variables. For example, I may not want to replace a missing value with just the mean across the board. If the patient that has the missing value is like female, then maybe I want to do it the mean over only females, especially if it's something like height or weight or something that we know that there's like some like sexual dimorphism. Age, we want, you know, people of the same age. There's a lot of different ways to do that. If there's time, we may talk about those. Something like a KNN imputation or some other fancy imputation. But for now, we're just going to do the mean value that we always have been doing. Okay. And actually, now that I think of it, that's the only thing we can do because we don't have any clinical covariates, right? And we can't use the labels to help us. I don't like, oh, only put in the average of all those that had the AML. You know, all the AML patients fill in with their missing data. You really can't do that because what are we going to do for the testing set? You're in principle not supposed to look at the labels. All right, so we looked at the data before. We know that it's pluses and minuses, so zeros do mean something apparently, but certainly an inf, like nothing should be infinite, right? And that happens when they were normalizing. I think maybe there was a divide by zero somewhere or something like that. So how would we remove any infinites in the training set? How would you guys do it? It's gonna be another replace function. So I'll give you that much. So train.replace. What are we replacing? Is what with what? Like what with what? What goes here? So the imps, so for the sake of time, right? So imps, we can use the numpy definition, right? And I think they'll be there. So numpy.inf. So we want to replace the numpy imps with what? I'll leave this part open to you guys. So what we're going to do here is we're going to replace the missing values with the mean. Does nothing work? No, because that's just going to be a blank space. So when we impute the mean here, so I'll give you another clue here. We're going to do something like, remember how we imputed with the mean before? It wasn't with a replace. It was with a, not replace, but do you remember what the function was? The function here. No. Simon or Henry, do you guys know? We've done this so many times, so you can look back at how we imputed with the mean. Okay. Fill, yes, yeah. We're gonna fill, and well, there may be missing values, right? And so fill, like if I replace these infinites with some value, right? Like a, then I can say fill the a's, right? Fill the a's with like the mean, something like that. But that gets a little clunky, right? Last time we did fill NA, right? So that's easy because now anywhere you have a missing value, a true NA, then we could fill its value with the mean, right? So in this case, it'd be something like train, the values, right? And like the mean. Like, I don't feel bad because I think this is exactly how we wrote it before. I don't know. So if that's the case, if I'm going to be ultimately filling the NAs, then what would be a convenient thing to replace these imps with? Anyone? What should I can't make them zeros, because if I make them zeros, there's already zeros in the data that means something. So I don't want to somehow like fill the zeros with the mean. That's an error right there. That's a dot. Okay, we're gonna want to put nans, right? So what I'm doing is I'm replacing these imps that'll give us problems with this and put in nans. So now, if there were any missing values, now all these other ones, these unreasonable, unrealistic values are also nans. And now I'm going to replace all those nans with the mean. Does everyone see what I just did there? This is like a common trick. You'll see it over and over and over and over and over, right? The last thing you do is to impute all the nans, and then you replace all the weird data, like, you know, anything that's misspelled, replace it with a nan, or anything that's like, if zeros were a bad number, we did it last time. We replaced that with a nan, and here imps are problematic. So we'll do the same thing here for the testing set, right? Whatever we do to the training set, we have to do to the testing set. So that's it. Okay, is everyone okay so far with what we've done? Yeah? Like type a yes if you have, because we really can't move on. We're just imputing values here. No reply. Yeah. Everything is good. Okay, great. So we're all on board. Let's run this piece of code. And okay. So we've treated the data. So like, here's an open question then, like, how would you go about visualizing the data, right? So we just finished formatting it. I think we're done formatting it. How do I visualize it, right? I can't just make a table one, but why? Exactly, it has way too many dimensions. I can't like write a table with like 7,000 rows or whatever, right? And even if I could, like, how would you even read that? Like, how much information would you be able to get from a table that's just this wall of text like that, right? Not much. So like, what's in the cards now? Like, what do we need to do then? What's on the table? Dimension reduction. Perfect, John. Exactly. We can't get around it, right? There's 7,000 predictors. We need to do some dimension reduction. So I've chosen to do PCA. I think that if you could do like dimension reduction by doing some feature selection, right? But I think that even something like Baruda or something on 7,000 features is like, I think that would take way too long, because it's going to try a model, like Baruda is going to try a model with all of the features included, right? And then it's going to do it, and it's going to iterate like hundreds, if not thousands of times. I think that would be prohibitively expensive. It will run like for weeks. But if you did do that, I mean, be my guest. If we did do that, the result will be that it would pick up those genes that had a chance to predict the outcomes, right? That's statistically better than just noise, than shuffling them. That's one way, but we're like, we can't do that. So let's do a PCA, right? So the principal component analysis, what we're going to do is we're going to transform the native representation, right? This gene representation, transform it into another representation such that in that new space, every one of those dimensions are now orthogonal, right? In other words, that they're like perpendicular lines. You could think of them like vectors. A vector of these genes in the gene space, and they all point in orthogonal directions. In other words, we're going to remove any correlations that are in the gene data, right? And the idea is that by removing correlations, like correlations are like basically unnecessary data, right? Redundant data, that we can describe most of the picture without having to use every single one of those dimensions. Like if the data was highly correlated, I can compress the 7,000 dimensions into, well, who knows? Let's just say 10 dimensions, right? If the data was highly correlated. So that's what PCA is doing. It's a change of basis, right? It's you're changing the representation of what the data is. So, so this is where we're going to have some heavy Googling going on. All right, guys. So right here, we need to load up from, I need you guys to look up in sklearn. We're going to need a pre-processing thing. Go look up something called pre-processing and look up something called PCA and tell me how to import that code right here, because we're going to need it. Since I'll throw you a, well, yeah. So I'm looking for something that says something like from sklearn import what? Oh, sounds, yeah, there you go. Decomposition import PCA, perfect. Yeah, decomposition. I hope I spelled it right. From sklearn, oh, yeah, you're right. From sklearn dot decomposition, I'm gonna import PCA. Yeah, is it capital like that? I think it is. I'm also Googling it. Yeah, import PCA. Okay, I think we did that one. All right, now we need the pre-processing from sklearn. So from sklearn, I mean, it's straightforward. Import pre-processing. Okay, this is a question, you guys. What is pre-processing? We've seen it once before, but what is this doing? Or what does this do? That's my question to you guys. Yeah, we're gonna use this to scale our data, right? Basically to like z-score it later. Because when we change representation, who knows what the scaling is now, right? Like, so okay, so let's move on. So we're gonna do a PC analysis, right? For all the data, and yeah, that's true. This should only be done on the training data. Okay. I've chosen for us, we're gonna only do 10 principal components, the first 10 principal components. Okay, so we need to define, this is where you Google, because I don't think you've actually seen this before. So we're gonna define an object called PCA, and it's gonna be this PCA object. And we need to like declare it, right? We need to create this object. and we need to define this number of principal components. And I need you guys to look up what the syntax is. So things called PCA. So I'm sure that it's going to start like this. Yeah, it's that simple. Yeah, n components equals npc. All right, so let's do that. N components is equal to n little n, npc, and also because it's stochastic, I'm gonna put a random state in there. Random state. I'm gonna set it to our seed that we always set in the front. It's like some prime number I choose. So yeah, so now we made the PCA object, right? Okay, and we're gonna define a standard scalar. This is the thing that's going to scale our data, right? I'll just do this for you guys, but you would do just like you did for PCA. You look this up, right? So you say from processing, right? That's this thing that we just pre-processing. We're gonna look up this thing called standard scalar, and that's it. We just created the thing. There's no arguments. So now we've created this object that's going to, well, help us scale our data. Okay. So, so we need to now use this scalar to scale our original data. I think it's already been scaled, but you never know. So X scaled, I want to scale the training data. So I'll call this scalar. All right, and we need to fit it. So what's the syntax to fit the transform? You should be like Googling furiously right now. Yeah, no, fit train, no, but fit transform. Yeah, but we definitely are fitting. We definitely are fitting because this thing hasn't been, like Zscaler needs to know, like, well, where's the mean and what is the standard deviation that I'm going to be applying, right? So fit, but we're going to fit the transform, fit and transform the data, right? So what is the thing that we're transforming? Well, it's just train. It's the training data, right? So I want you to not only just fit your data, but transform the training set and then spit it out as X scaled. Okay. And then now I want to train the PCA on that scaled data. Okay. So I mean, it's going to call that PCA object, right? PCA. And it's going to be the syntax is actually the same. It should be the same. Do you guys see in your like Googling like how to fit transform? Yeah, exactly. Yes. So I want to fit and transform and do the principal component like transformation on this scale data. So I probably could have gone away with not doing this, but you never know. And now I'm certain of it. Moreover, we fit this scalar. So now I can use whatever transformation I used here. I can use that very same transformation on the test set. Yeah, so okay, so here I take the scale data and I fit this PCA and go ahead and do the transformation. It knows to use only 10 principal components, and so X-train PCA should have only like 10 features, right? Here, I'm just going to apply the scalar and the PCA that we already fit. I'm going to apply it to the testing set. So the first thing we do is this call that scalar, and it's just now fit. No, it's not fit, it's called just transform, I think. I'm looking it up. Yes, it's just transform. Okay, you would have done the same. You just like look up just the transform, and what am I transforming? The test set, right? Yes. And then I'm going to call, oh, this is the PCA. I haven't scaled it yet. Oh, look. Okay, great. So this is basically this transformed, the scaled test set. That's what goes into the PCA, right? So I could probably do something like PCA dot transform. And what am I transforming? I'm transforming the scaled test data. Does that make sense what I just did? Like, so PCA has already been fit, so I'm just going to use it. Like, you've already been trained, use the same transformation that was trained on the test set, use that to transform the test set. I'm sorry. And what's going into it is the scaled test set. And we're going to use that same scalar refit. Okay, what am I doing here? I'm gonna, just print out the shape of train PCA. So yeah, so this should have, it should have the same number of patients, but only 10 features, right? So let's have a look. Let's hope there's no errors. Yeah, look at that. 38 patients, 10 features. Great. Does everyone know what we just did there? In the test set, we can print out the shape of the test set too, if we're curious. Test PCA shape. And it's 34 patients, but it's 10 features, these 10 principal components. These are our new features. We've engineered these features, right? So this is an important thing to do. These transformers, you really should only fit those with the test training data. It's a common mistake to just fit all the data. It's a common mistake to just transform all the data and then move on to your analysis. That's technically an error. So the way we did it is like, the proper way to do it. At least you won't get called out on it. Okay, so now we've transformed these features into this new representation, the principal component representation, right? And now we can visualize it. We can go ahead and do a table 1, but it's not going to mean too much because, like, sure, it'll tell us how these principal components are associated with the labels, but you basically can't interpret them, right? Like, it's just a linear combination of every single gene. But we could plot their distribution, right? And that'll inform us as to what kind of model we can use. Okay, so let's go ahead and do that. We're gonna plot those distributions, and I wrote that part for you here. We're using Seaborn. This KDE plot is the kernel density function we've always been using to sort of plot the densities. I'll walk you through this, and then you can tell me how to rescale the features. But basically, it's for every principal component in the range of principal components, so 1 through 10 or 0 through 9. We're going to plot the data in the testing set, right? So X test PCA in the new representation. We want all the rows, all the patients, and only that principal component, right? So the first plot should be principal component 0, and then 1, and then 2, and then 3. And then, yeah, this is just a legend, and then just show the picture. Okay, so that should work. We need to, you know what? I bet we can get away with not rescaling. So let's have a look at that. Is everybody comfortable with what I've done so far? I mean, I'm just plotting, I'm visualizing the data, right? So this is what the density plots look like for the 10, 0 through 9, 10 principal components in the testing set. So it's not mean centered, right? Well, the mean's somewhere over here. It goes from 0 to 100. This one goes from 0 to 80. This goes from 0 to 40. Yeah, guys, we're gonna have to standardize these. In order to compare them, they all have to be on the same like footing, right? They all have to be on the same scale. And by the looks of it, we're gonna have to scale. So now also, are we dealing with bimodal stuff? Are we dealing with, there is an argument to say like, yeah, there's two things going on here. It looks like there's a shoulder here, but since the density of this is like 0.02, I'll leave this. And if this was rescaled, like if this went from 0 to 1 instead of from 0 to 100, it's not like the tails are going off in different orders of magnitude. So I actually wouldn't do anything other than z-score this. Here, I'm really tempted to like split this, but it's not really like, when you split it, you mean to do something, right? Like you mean that this feature split here means something distinct from over here. And since we're dealing with principal components, what does that mean? That's like saying the vector of genes in this representation less than 20. What does that mean? That has no units. So you know what? I'm not going to split or categorize this data. And I think, so right now, I guess that only leaves are their tails. And I don't see dramatic tails. Not really, not even this and not even this. So I think we have to just z-score this, use that standard scalar. So we do need this. All right, guys, so how would I go about scaling this data? I need to scale X test PCA. And I guess I need to scale the, oh, why does it say test? It should be train. Oh, well. Yeah, it's the same deal. So maybe someone can help me scale this data. I'm basically just do this. It's basically this function here. We're going to use that scalar. We already defined a standard scalar, so let's go ahead and use it. All right. So it's going to read something like X train PCA, right? The train and the test PCA and the new in the PCA representation. I want this to be, I want to apply that scalar that we built, and we need to refit it because it's new data. Fit and go ahead and transform. Fit and transform X train PCA, right? Yeah, X train PCA. And I suppose do the same thing for the test. And I guess whatever I did to the train, like I should use that one, so I shouldn't refit. Test PCA. This seems reasonable to me. Does anybody object? Is anyone confused? Like, what is he doing? Why is he going on and on about this? Okay, so I ran it and then I replotted the train data, and now it's mean centered and it has a unit standard deviation. And so you see how they're all like singleton, like at their extremes. So they're all on the same scale. This is great. I think that's fine. I think that's fine. All right, guys. So we've so far have basically did that the worst part of the ML, and that's the data cleaning part, right? And what have we learned so far? Well, we've sort of chosen to use this representation, but we never justified it. We just said we do it because that's what I know how to do, right? And then given that, I was able to get data that looks reasonably like, you know, like Gaussian functions. So I don't see why they should have a big issue throwing this into like a logistic regression, like a linear model kind of thing. So that's what looks like in the cards, that we're going to build a logistic regression model on this, on the data in this representation. And I suppose we can always increase the number of principal components. Okay, so I hope you guys all were able to understand what we just did there. And I want you now to use that sort of understanding on the real data. Okay, so now let's take a minute. I'll pause right here for any questions so far. Please let me know if you're good. Just say I'm good here. I mean, there's few people in the audience, so it should, should move really quickly. Yeah, you're good. John's good. Great. Okay. So there's a more challenging leukemia data set, right? And it's part of this dream challenge. I provided the link in the notebook, and it's through here in synapse.org. To get it, you're going to have to register. So you just follow the directions to access the data, and then you request access. Okay, that's how that works. So you have to request the data, and I'll explain a little bit what's going on in the data set. So in that data set, there's actually multiple outcomes, right? There's it's still leukemia, but there's outcomes for relapse. There's outcomes for how the patient responded to treatment. And I think there's maybe a few other ones. So we can do both classification and regression tests with this one. And what is in there? So there's about 200 patients, and it includes, again, this highly dimensional genomic data in addition to clinical covariates. So we're going to have to do some dimension reduction in the genomics, and we're going to have to do something about these clinical covariates, right? We'll treat them in the usual ways we have done so far. So our challenge here is to develop a model that addresses these outcomes, right? And we're going to do this all end to end. And we have these 2 weeks. I mean, we have 4 weeks. You have 4 weeks to do it. And we'll, in the beginning of every next time we meet, I'll open the floor and see how you guys are doing. We have to touch base because I can't have you guys just go off on the deep end. And let's see if we can get this done in about 4 weeks. Okay, so yeah, we're going to review, and then at the end of the 4 weeks, we'll review the analysis you guys come up with. So these are basically the beats that your analysis should follow. Okay, so the first thing you have to do is format the data, just like we did today. We want observations in rows and features in columns. Okay, and then look at the data and see. You're going to have to do some manual, like, is there any data in there that you can manually exclude? Things like bookkeeping variables, right? Like, we don't need to know the patient's name, but we should keep their age, something like that, right? They're de-identified, so they don't have their names. But patient numbers, stuff like that. And if there's some data in there that's just like, yeah, like sample collected on day so-and-so, probably doesn't matter. And then once you have it, normalize the data, right? Make sure that's like mean-centered, unit variance, kind of stuff like that. Treat any missing data, right? You can interchange those two probably. I don't think it matters too much. And the data is not partitioned. Actually, I actually don't know this. Simon or Henry, do you know if the data has been partitioned already into training and testing sets?
Yeah, it has been. Yeah.
Okay, so great. So you don't have to employ a partitioning scheme. It's been done for you. That's relieving. Okay, so what I want you guys to do is take those clinical covariates and do some feature selection. You can, since there should be a finite number of them. And those features that you select that are associated with the outcome, these are going to be the variables that you're going to adjust for, right? Because they influence the outcome, right? And for the rest of the omics data, we're going to do dimension reduction, okay? You could do PCA, or if you think of something fancier, be my guest. I'd love to hear it, right? Okay, so based on all of this, when you look at the data, you will choose a model, right? If it's a classification task, you might get away with a linear model like logistic regression if your data is normally distributed. If it's not normally distributed, you have to do something different, like maybe a tree-based model. Be interesting to see. And if we do one of the other outcomes like a regression task, then it would be linear regression if the data is normally distributed. You know, if you look at the like heteroscedasticity of a linear model. So once you choose your model, then go ahead and you train it, right? You train it, and then you calculate performance metrics. That's going to be like in regression, it could be something like mean squared error. For classification, you could do something like the binary cross entropy or log loss or accuracy or F1. It's not just enough to just pick one. You have to justify why I picked accuracy, right? So like, you know, things like, well, we know that accuracy like breaks down when the labels are imbalanced, right? And then once you're all good, once it's all trained, then you picked your metrics and you're all happy, then go ahead and make some predictions. Make some predictions on your testing set and interpret those results. So I think it's a fun task to do in 4 weeks. Okay, so I had saved this next bit here in case we had the time to do it. I really want to talk about this. It looks like we have some time. So, but before we get into it, do you have any questions so far? No questions? You good? Okay, we're gonna keep touching base on this. All right, shall I move on? All right, guys. All right, so we changed we realized that we can't just look at the gene data in its raw form, in its native representation. It's just too big. We have to do some sort of dimension reduction, right? We have to reinterpret the data, or sorry, represent the data in a different way. PCA is one way, but I find PCA to be very difficult to interpret, right? If your goal is merely to make a model that's predictive and you don't care what the elements are that it uses to make those predictions, as long as the predictions are good, then PCA maybe is fine. But rarely, I think it has. This is, but rarely is that the case. Like in like the biology research we do, right? You look at your model and then you probe the elements that it's using to make its decision to inform you of something, you know, about the nature of biology, right? Like, and so principal components are like terrible for this. So I believe that if you were to say can we represent the data in like maybe a pathway representation, right? Take those genes and then somehow take that gene data and somehow find a number for pathways that describe how, I don't know, how normal that pathway looks in this individual. Does that make sense? Like, imagine that there's a pathway like the TCA cycle, right? And it's made up of like what the eight metabolites in this case, right? For gene data, I guess it would be the enzymes that participate in the pathway. And let's say that on average, most people have, you know, enzyme A certain value. and a patient comes in and you measure their gene expression for that enzyme in that pathway, and it's way off the scale. It's either underexpressed or overexpressed. Maybe there's a way to represent the dysregulation in that pathway at the patient level. So here's my idea for you guys to try. Let's look up those genes, right? Let's look them up, like let's get their KEG IDs and look up those genes and then find out which pathways they participate in, okay? And then for every one of those pathways, I select only those genes, right, that are in our data set, those genes, and then let's do a PCA analysis on only that subset. What is a PCA analysis going to do? It's going to tell us how those gene expressions fluctuate. It's going to describe the data, right? It's going to describe how they fluctuate and the major modes of fluctuation. So now if we choose only the first principal component of that PCA analysis for that only that pathway, we can describe each patient, we can project them on this fluctuation. So in the major mode of fluctuation of this pathway, where does this particular patient land? Is he right in the middle, just like everybody else, or is he on one extreme of like underexpression or overexpression? Okay, does that make sense? So instead of doing a PCA on all the data, I'm going to do PCA on just those metabolites that participate in a particular pathway. And now I have and only use that first principal component. So now I have a number for every pathway. Does that make sense what I just said? All right, we're going to change the representation into a pathway representation. Okay. So now is the time to ask questions, right? Okay, so those gene IDs in the data that we have, we're in this, I don't work with gene data. They're in this format. Maybe Simon or Henry can tell me about it, but I was able to find a web app to convert them into KIDs that I'm familiar with, right? So that's what we're gonna have to do, right? And there's probably an API, but I couldn't be bothered. So we're gonna use this tool right off the web, right? So if you click on it, it brings you to gProfiler. Have you guys used this, Simon or Henry?
It's not how I would personally do it, but I know people do use this one.
Oh, okay. Well, like the idea, the principles should be the same. This is just the way that I used it, that I used. So what goes in here are going to be those gene ascension numbers in that weird Affy matrix or whatever format. And I describe what to do here. So let's just, so we're just going to copy and paste those ascension numbers, put them in that query box, and we're going to ask to look for, give me the KIG enzymes, right? So we're just converting, all right? So it's all human, it's for humans. And so what we want here are the KIG genes or the KIG enzymes, something like this. Is it alphabetical? Looks like it. Ah, here we go. KIG enzyme. Okay. And I'm gonna need to put those ascension numbers in here, right? So we saved them, but I think it'd just be easier if I just did this, right? The training set. Oh, let's look at it with yeah, let's just open it with like Excel. I know I'm not sharing my screen, but all I'm doing is copying and pasting that column in the thing. This. Open. Oh, I need to find it. Jeez. Okay, fine. Where is it? Module mine, data, train. Maybe I'll share my other screen so that you can see what I'm doing. I've just opened up that training set data. We want this column. So just going to copy it and then go back to the Jupyter notebook. This. Yes. Here. Put it all in there, all their names. It's like 7,000 or whatever. You don't need the header. Just go with that and run the query. I'm sure you could do this programmatically, but I'm going to go ahead and do that for you. And it's going to give you an option here to just, so, oh, I got a bunch of nans. That's not good. I didn't get nans the last time I did it. Is there something wrong here? I didn't get nans. Homo sapiens, cake enzyme. That's right. Homo sapien, yes. That's fine. Is something being copied incorrectly? Yeah, I'm getting nans. Last time I got all these to run. For the sake of time, I'm just going to pull up my old files. I probably copied something incorrectly. Gee, I wonder why it's not working. I'm pulling the old data out right now. Maybe it has to do with this first one. I don't see why that would be the issue. I have my old data, so I'll pull it out. All right, so okay, I'm just pulling out the old data I have, and I'm going to file, save as gprofiler, and I want this in okay, so I'm just pulling my old data. Sorry, guys. There's always going to be technical issues when you're on the spot here. I'm pulling the old, my old data. I did exactly what that was. I just copied the column and remove the header, and I get this file, this gprofiler Homo sapiens CSV, and this is a terrible way to look at it, but well, I'll show you in the notebook. It has the gene name in that AFI matrix like format, and then it gives you the KEGG, the gene name. Okay, so I can now just look at it, and that's what we're going to do here. Okay, great. So these are the genes that were in our original data set, right? And it has given me now the gene names associated with them that I can look up in KEGG. Okay. It also gives you a description. But notice that for multiple gene entries, they're the same name. So what we do now here is that we can follow this KEGG tutorial, and it tells you how to basically search for pathways by a gene name, okay? And so I'll just walk you guys through this, right? So we're gonna install this package called bioservices so that I can import the KEGG interface here, okay? Okay. And so now I'm gonna start this interface, and I'm gonna then, like, this is an example how to get pathway by gene name. So I use that gene name for the human species, and you get something that looks like this, right? The output is, these are the pathways, right? These are their IDs, and this is like their description, right? This is glycolysis, metabolic pathways, carbon metabolism. So what were we able to do here? From each for each gene, for each enzyme, I can now get a list of the pathways that it participates in. Okay, so what I'm going to do is I'm going to get the unique genes in that data, that gene profile data that I downloaded. Okay, and I can comment this out and run this, and notice that there are like 4,000 unique genes in that file. Okay, so for each one of those genes, I can then look. I can then ask, what are the pathways that you participate in, and then start making a list, right, of all the unique pathways. And when I have a unique pathway, I'm going to add that gene to that list. And when I go to the next gene, if it happens to participate in the same pathway, then I add it to the list. And so at the end, I want something that is a series of pathways and the genes that are associated with it, right? For the sake of us, I'm just going to truncate this list of 4,000. I'm just going to truncate it to like 50, okay? So genes is now 50 genes, okay? And so this is what we want to do here, okay? I'm going to create a dictionary that's going to hold the pathway to gene mapping, okay? And so it's empty right now. And what I'm going to do is I'm going to loop over all the genes in that gene list that I just made, right? So we want to get the pathways associated with the gene. And so for the sake of time, I'm going to sort of like go through this with you guys for you. So we want to get the pathways associated with the gene, right? So we call that function that we just made right now. So it's called pathways. And we're going to, I mean, we gave the example. So it's just something like this, right? The pathways, so that's this output. It's like a dictionary, right? So the pathways is the output of this. Get pathway from gene, but instead of that specific gene, we're going to use the gene in this gene list, okay? And it's a string, it's expecting a string, okay? Now we want to loop over all the associated pathways, right? So all these pathways that are associated with this gene. So it may be that it doesn't find something and it'll throw an error. So that's what this try and except function is. So try to do this, and if you can't, well then just throw your hands up in the air, but don't crash the program. So for every pathway in that pathways dictionary, and so pathway is the key, and this is the description is the value. We're interested in the keys. Check if that pathway is in our pathway dictionary that we're building, right? So if it's not, if the pathway is not in the pathway dictionary, then we're going to append this pathway to the gene list, okay? So I'll just code this up for you guys because we only have like 4 minutes left. So that should look something like this. So pathway dictionary, we create a new entry called pathway, and we're just going to tack on a list that's initiated with the gene. It's a list with only one thing in it, that one gene. Okay. And then it tries the next pathway. If it's, let's say that it's not a new pathway, it wouldn't be for the same gene, but let's say that it's not a new pathway, then don't create a new list, just extend that gene list associated with that pathway, right? So that's where this comes in here. We'll write it right in here like this. So pathway dictionary for that pathway that we know, extend its gene list with this new gene that we just got. Okay, I'm gonna sort of plow right through because we're running out of time. So it's looping over the 50 genes. So this is incredibly slow. Does anybody know why it's incredibly slow? Why no one would ever realistically do it this way? So it's for loops. For loops are terrible. It's a terrible look. It's like so many nested for loops, and we want to do this for like 4,000 genes. There's a better way to do this. I'll leave it up to you. So let's display this dictionary as a series, so that I could just look at the head, right? And so here we are. These are all the pathways, and these are their associated genes. Okay. So the idea now is that these are going to be our new features. These pathways are going to be our new features. And what you want to do is get these genes and only these genes that participate in this pathway and do a PCA analysis, right? So look these genes up in our original data, find the columns that they're in, pull that data out, do a PCA, and only get the first principal component. That value is going to be the value for that patient for this pathway feature. And that's how we're going to do in the new pathway representation, which in principle will be more interpretable. You could start talking about predictive pathways instead of just, principal components of every single gene. And moreover, it's at the individual level. For each patient, there's a pathway dysregulation score that's associated with them. And I'll stop here because we're out of time. Yeah, this is the fun bit. This is another way to change the representation of your data, and I think it would be more predictive. Okay, guys. Questions? Concluding remarks? You guys are gonna now you're brimming with anticipation to pull the dream data set, start working on this capstone project. Well, okay then. All right, guys. It's been great talking to you guys. Next week we'll work with the PCA data and we'll start training a model and in the next week. And then we'll go on to computer vision. So it should be really exciting. Yeah. Yes, my pleasure, Kim. Kim, John. Why I never call you Kim? There you go. All right. Okay. And a sign off then.